roar begins deep in the ground before it reaches the air. The launch pad trembles, steel bolts shiver, and the sky fills with a thunder that seems almost alive. Fire blooms beneath a towering rocket, bright as a newborn star, and the Earth itself seems to resist letting go. Slowly, painfully, the craft begins to rise. The engines scream against the weight of an invisible force that has held every ocean, every mountain, every living thing for billions of years. It claws upward, meter by meter, a fragile column of metal daring to defy the planet that made it. The people below watch with awe, their eyes following the trail of flame that stretches into the clouds. In that moment, they are witnessing a battle as old as time itself, the struggle to escape the grip of gravity. We are born in a gravity well, a deep invisible valley carved into the very fabric of space by the mass of our world. From the moment we take our first step, every motion we make is measured against this unseen pull. It keeps the oceans from drifting into space. It holds the air that we breathe. It tethers the moon to its orbit and shapes the dance of every planet around the sun. It is everywhere and nowhere, silent and absolute. And for all of human history, it has kept us bound to this small blue sphere. The invisible cage we live in is not made of bars or walls. It is woven into the geometry of space itself. We do not feel it when we stand still, but it is always there, pressing downward with a quiet insistence. Every stone that rests on the ground, every bird that lands on a branch, every droplet of rain that falls, all of them are participants in the same endless negotiation between motion and restraint. We exist in balance with gravity, our muscles and bones shaped by its pull. Our hearts evolved to push blood upward against it. Without it, our bodies would drift apart. With too much of it, we would be crushed. Yet the dream of leaving Earth has always burned in the human mind. Long before rockets or physics, we looked to the sky and imagined freedom. Wings of fire, chariots of the gods, machines that could break the hold of the world below. But gravity is not an enemy that can be defeated through brute strength alone. It is the deepest law of nature, the expression of how mass bends space and dictates the motion of everything within it. To escape it is to challenge not just weight, but the structure of reality itself. When a rocket launches, it is fighting more than its own mass. It must overcome the gravitational potential energy that binds every kilogram of fuel, every bolt, every human aboard. The engines must release enough energy to climb out of a pit so deep that even light feels its pull. This is why the first moments of a launch are the most demanding. Near the ground, gravity is strongest, and the thick atmosphere drags against every motion. The engines roar with a fury equal to millions of horses, consuming fuel at a rate that defies imagination. In those first few minutes, more energy is spent than in the rest of the journey combined. And still, despite all that power, the rocket rises slowly. It does not leap into the heavens. It inches upward, trembling, as though reluctant to let go. The flames that trail behind it mark the price of every meter gained. The noise, the fire, the trembling ground, all of it is the sound of energy being poured into the battle against the planet's embrace. The people watching see triumph, but what they are truly witnessing is a delicate and brutal exchange. Energy traded for altitude, fuel burned for freedom. What makes this struggle so difficult is not the strength of gravity alone, but its persistence. Gravity never stops pulling. It does not fade when the engines ignite or lessen with hope. The higher a rocket climbs, the weaker the pull becomes, but it never truly disappears. The only way to break free entirely is to reach a speed where the curvature of space no longer bends the path back toward Earth. That speed, the threshold of liberation, is known as escape velocity. But before one can understand that number, one must understand what gravity really is. For centuries, humanity tried to describe this invisible force through observation and intuition. Ancient astronomers noticed that the planets moved in repeating patterns. Their paths curved around the sun in ways that hinted at an unseen hand guiding them. Isaac Newton gave that hand a name and an equation, describing gravity as a force of attraction between masses. He showed that the same pull that made apples fall also kept the moon in orbit. Yet even Newton did not know why this force existed, only that it worked with extraordinary precision. In the centuries that followed, physicists began to look deeper. They realized that gravity is not just a force pulling objects together, but a feature of the universe itself. Space and time are not rigid backdrops, but flexible fabrics that bend in the presence of mass. A planet curves the space around it, and what we call gravity is simply the motion of objects following those curves. The more massive the object, the deeper the curve, and the harder it is to climb out. This is the reality of our invisible cage. We do not sit on top of Earth so much as we dwell within a depression in space. Every step we take upward costs energy. Every climb to the mountain peak is a small act of defiance against the curvature of space-time itself. When we launch a rocket, we are attempting to roll a stone up the deepest hill in the cosmos, knowing that if we falter for even a moment, gravity will call it back down. This understanding transforms the idea of escape from a simple matter of thrust into a profound encounter with the nature of reality. To leave Earth, we must not only overcome a force, but outwit the geometry of the universe. We must inject enough kinetic energy into a spacecraft so that its path bends outward forever, never to return. And that, more than anything else, explains why leaving home is so hard. In the silence that follows a successful launch, when the rocket has pierced the upper atmosphere and the engines throttle down, the Earth below begins to shrink. The blue fades to black, the horizon curves, and the cradle of humanity becomes just another sphere suspended in a vast sea of night. It is beautiful, fragile, and impossibly distant. Every astronaut who has seen it describes the same feeling: awe mixed with humility, the realization that escaping gravity is not a rejection of Earth but a reminder of its power. From this vantage, one truth becomes clear: gravity is not a cage built to confine us. It is a reminder of where we come from, of the connection that binds all matter, from the smallest grain of sand to the largest star. To understand it is to understand ourselves, and to truly escape it, we must first know what it is. The story of gravity is the story of motion itself. To understand why escaping it is so demanding, we must first step back and ask what this force truly is. Isaac Newton imagined a cosmos in which every particle in the universe pulls on every other particle. The strength of that pull depends on how massive the objects are and how far apart they sit. He saw the Earth and the Moon locked together in an endless exchange of attraction, a kind of invisible tether made not of matter, but of pure influence. The same law that draws an apple to the ground also bends the path of the Moon as it circles the Earth. The genius of Newton was that he realized no boundary separates the heavens from the ground beneath our feet. The same physics governs both. For a long time, this picture seemed complete. Yet the more carefully scientists measured the sky, the more subtle inconsistencies began to appear. Mercury's orbit did not fit the predictions perfectly. Light itself, which by Newton's reasoning should have no mass and therefore feel no gravitational pull, was found to bend around massive stars. These small mysteries hinted at a deeper truth. When Albert Einstein reimagined gravity, he did not treat it as a force acting across distance, but as a shape, a bending of the space and time in which all things exist. In his view, matter tells space how to curve, and curved space tells matter how to move. If we could see this curvature directly, the Earth would appear as a vast bowl in the fabric of the cosmos. The heavier the planet, the deeper the bowl. Objects placed near the rim slide inward, not because they are pulled by an invisible hand, but because the path they follow naturally curves downward. In this way, gravity is geometry made real. The Moon stays aloft because it moves fast enough sideways that it keeps missing the bottom of the bowl, forever falling, yet never reaching the Earth. The deeper one lies in a gravitational well, the harder it is to climb free. Near the surface of the Earth, we sit at the bottom of a deep pit carved by the planet's mass. Every step upward requires energy to move against the direction of curvature. The higher we climb, the easier it becomes, but the slope never disappears entirely. A rocket does not break from gravity because gravity weakens. It escapes because it gains enough speed to move along a path that no longer curves back toward the Earth. This concept, that motion and geometry replace the idea of force, changes how we imagine escape. When a rocket lifts off, it is not fighting an external pull, but climbing out of a valley in the cosmic landscape. Its engines push it up the slope, converting chemical energy into motion until eventually the curvature flattens and the craft can glide outward on its own. The required energy is immense, not because gravity is unusually strong, but because space around Earth is deeply curved compared to that of smaller worlds. For perspective, think of the Sun's influence. It is far more massive than the Earth, yet the Sun's pull on us is weaker than Earth's own gravity at the surface, simply because we are so distant. The force decreases rapidly with distance. Double the distance, and the attraction becomes 4 times weaker. This is why astronauts in orbit still feel the Earth's gravity. They are only a few hundred kilometers above the ground, far from being outside its reach. Gravity defines more than just the motion of rockets and planets. It governs the structure of galaxies, the collapse of stars, and the growth of black holes. In the presence of extreme mass, curvature becomes so steep that nothing, not even light, can climb out. The event horizon of a black hole marks the place where escape velocity equals the speed of light itself. Here, gravity is not just a background influence, but the dominant feature of reality. Time slows, space stretches, and cause and effect begin to lose their familiar meaning. Compared to these cosmic monsters, the Earth's gravity is gentle. It allows water to flow and clouds to drift. It gives us weight, but does not crush us. Yet that very gentleness hides its persistence. Gravity cannot be switched off. It does not fade with time or distance in any absolute sense. Its influence extends infinitely, merely diminishing as the square of distance grows. This is why there is no true edge to Earth's gravitational field, only points where other forces, like that of the Sun or the Moon, become stronger. Understanding this persistence helps explain why the challenge of escape lies not in the power of engines alone, but in the relentless nature of the geometry we inhabit. Every kilogram of mass on the rocket is a participant in this geometry. To lift it 1 meter higher means supplying energy to change its position in the curved landscape. To leave the planet entirely, the rocket must provide enough energy to flatten its path into a straight line that never bends back. That straight line corresponds to a particular speed, the escape velocity, and reaching it is the key to freedom from Earth's grasp. In a sense, we do not defeat gravity when we launch into space. We negotiate with it. We use velocity as leverage, trading motion for distance. The deeper our understanding of the geometry, the more efficiently we can find paths that require less energy. Orbital mechanics, slingshot maneuvers, and gravitational assists are all examples of this negotiation in action. By learning the contours of the cosmic landscape, we find ways to slide along its curves rather than climb against them. And yet, every journey outward begins with the same act, rising from rest at the bottom of the well. This is why the first few minutes of a launch consume such staggering amounts of fuel. At the surface, gravity's grip is strongest, and the atmosphere compounds the struggle. To an observer, the rocket's ascent may appear smooth, but within the capsule, astronauts feel the crushing acceleration that accompanies the battle against both drag and weight. Each second of upward motion represents thousands of kilograms of fuel transformed into heat, noise, and motion. When the engines finally cut off and the craft enters orbit, the feeling is not one of weightlessness, but of perpetual fall. The ship is no longer climbing out of the well. It is circling the slope so rapidly that the downward pull of gravity is balanced by the sideways motion of its path. The astronauts inside feel free, Yet gravity still binds them completely. They are passengers in a perfect fall, looping endlessly around the world below. In this dance between motion and geometry, one truth stands unshaken. Gravity is not an enemy. It is the quiet architect of the universe, the unseen sculptor of every orbit and every tide. We escape it not by conquering it, but by understanding how it shapes the space we move through. The climb from Earth to orbit is more than an engineering challenge. It is a conversation with the laws that built the cosmos itself. To escape the Earth entirely, a rocket must achieve a speed so great that even if its engines were to shut down, it would never fall back. This threshold is known as escape velocity. It is not a magic number, but a precise reflection of how deeply our world bends the fabric of space. To climb out of the Earth's gravity well completely, an object must move at roughly 11.2 kilometers per second. That is about 40,000 kilometers per hour. It means traveling 33 times faster than a rifle bullet. Only then does the curve of its path flatten enough to stretch outward forever. This figure is born from the balance between two kinds of energy. On one side lies the kinetic energy of motion, the energy of speed. On the other is the gravitational potential, the energy stored in position within the planet's field. To escape, one must have enough kinetic energy to match and exceed the pull of that potential. If the rocket slows below that limit, it will fall back, tracing a graceful arc that ends in the same gravity it sought to leave. If it reaches or surpasses the escape speed, it will continue on forever, slowing gradually but never stopping, coasting outward until the planet's influence becomes too weak to call it home again. The magnitude of that number tells us much about the nature of the world beneath our feet. The Earth is neither too small nor too large, neither too light nor too dense. Its mass creates a gravitational depth that is both sustaining and imprisoning. It is strong enough to hold an atmosphere, to keep water and air bound to its surface. Yet that same strength means that leaving requires unimaginable energy. Were we on a smaller world, like the Moon, the same escape would demand only 2.4 kilometers per second, a mere fifth of the Earth's requirement. On Mars, it would be about 5 kilometers per second. But here, at the bottom of this deep blue well, the number remains stubbornly high. Every launch must reach it in stages. No single leap carries a craft from rest to 11 kilometers per second in one motion. Rockets accelerate gradually, burning through fuel that vanishes faster than any human eye can measure. The engines roar for minutes that feel like eternities, each moment adding a fraction to the total speed. The first stage pushes the vehicle through the thickest part of the atmosphere, fighting drag and pressure as gravity tugs relentlessly downward. When its tank's empty, it falls away, discarded to lighten the load. The next stage ignites, propelling the craft faster still. In this way, humanity has learned to climb not through brute force, but through a delicate choreography of energy and efficiency. Even so, escape velocity is not something a rocket must maintain at every instant. In truth, no launch achieves it directly from the pad. Reaching orbit first, moving fast enough sideways that the spacecraft circles the Earth without falling, is the initial step. From there, an additional push can lift the path higher, transforming circular motion into an ever-stretching curve. When the final engine burn provides just enough energy to exceed the gravitational potential, the spacecraft is free. It will not stop, not slow to rest, not fall back. It will glide outward along the eternal slope of space, joining the sun's wider domain. To visualize this, imagine rolling a ball across a vast landscape. If you throw it gently, it arcs and falls back. If you throw harder, it lands farther away. But if you throw with perfect strength, the ball follows the curve of the ground so precisely that it never touches down. It circles endlessly, like a satellite in orbit. Throw harder still, and the ball's path flattens, breaking free from the curve entirely. It continues away, slowing but never returning. That moment, when speed overcomes shape, is the essence of escape. Every object in the universe is caught in such balances. Planets orbit stars, stars orbit galactic centers, galaxies drift through clusters, all bound by invisible threads of motion and curvature. The concept of escape is therefore relative. A spacecraft leaving Earth's gravity remains within the sun's. Leave the sun, and it still moves within the galaxy's greater curve. There is always another well, another horizon of influence. True isolation is impossible. What we call escape is really a transfer, from one dominion to another, from one curve in space-time to the next. Yet for humanity, even that first escape carries deep meaning. To reach the speed of 11 kilometers per second is to convert fire and metal into freedom. It is to take matter born in the heart of the Earth and give it enough motion to defy the very laws that shaped it. When Voyager 1 left Earth in 1977, it was not merely a machine. It was a statement that intelligence could climb out of its own cradle. 40 years later, that tiny craft continues its journey beyond the influence of the sun, carrying a record of who we are, proof that life from one small planet found a way to move between the stars. The energy required for such acts is immense. To accelerate a single ton of mass to escape velocity demands over 60 billion joules, equivalent to the energy released by burning more than 1,000 tons of fuel. This is why every rocket seems absurdly large for the small capsule it carries. Most of what launches into the sky is propellant, consumed in seconds for a few minutes of acceleration. The rocket's slender tip, the part that survives the climb, represents a tiny fraction of the whole. The rest is sacrificed to the laws of motion. These numbers might seem discouraging, but they also reveal something profound. Gravity is not an obstacle placed before us. It is a measure of how deeply we belong to this world. The energy we must invest to leave it mirrors the energy that holds us together. To escape the Earth's pull is not simply to overcome a force, it is to momentarily rewrite the balance that defines our existence. Every rocket, every launch, every burst of flame is a reminder of what it means to live within the laws of nature and yet to dream of rising beyond them. When a spacecraft finally breaks free, silence replaces the thunder. The engines go still, and the motion continues effortlessly. The curve of the Earth fades into the distance, its blues and whites shrinking until the planet becomes a sphere, then a dot. The ship glides on in perfect balance, no longer climbing but coasting through the geometry of space. In that endless glide lies the triumph of physics and imagination alike. We are the first species to understand the depth of the well we inhabit, and to find a way, however costly, to climb out. It begins with an apple. At least that is how the story is told. A man sitting beneath a tree sees a fruit fall, and in that moment, he asks a question that reshapes the human view of the universe. Why should the apple fall straight downward and not sideways or upward? Why should the moon not do the same? That man, Isaac Newton, lived in a world where the heavens and the earth were thought to obey separate rules. Yet his curiosity bridged them. He realized that the same pull drawing the apple to the ground could reach across the emptiness of space to bind the moon in its orbit. From that thought came the law of universal gravitation. Every object in the universe attracts every other object, with a force that depends on their masses and on the distance between them. The greater the mass, the stronger the pull. The farther apart they are, the weaker it becomes. It was an idea so elegant, so complete, that for centuries it defined the motion of planets, tides, and even falling stones. The sun holds the earth holds the moon, and the moon tugs the tides of the sea. The cosmos became a clockwork of forces, each planet tracing its precise path under the same invisible rule. But even Newton knew he had described how gravity behaves, not what it truly is. He could measure its strength, calculate its effects, and predict its consequences, but he could not say why masses attract at all. What thread could stretch across the empty void and pull two bodies together with perfect accuracy? The question lingered for generations, unsolved and unsettling. Centuries later, another thinker would offer an answer so profound that it would redefine not only gravity, but space and time themselves. Albert Einstein imagined the universe as something more than an empty stage. Space and time, he said, are woven together into a single fabric. Mass and energy do not simply exist within that fabric, they shape it. They tell it how to bend, and in turn, that curvature tells matter how to move. Gravity is not a force that reaches out across space. It is the shape of space itself. If we could see this shape made visible, the Earth would not be a smooth sphere hanging in a void, but a weight pressing into a flexible sheet of space-time. The Moon circles, not because it is pulled by a force, but because it follows the curved path created by Earth's mass. It is the same reason that planets orbit the Sun, and light itself bends around massive stars. The universe is a landscape of invisible valleys and peaks carved by matter and energy, and every motion we see, every orbit, every fall, is an object sliding along those curves. To stand on Earth's surface is to sit deep in one of those valleys. The curvature here is steep enough to hold oceans and air, to keep our feet planted on the ground. Climbing a mountain means moving slightly higher up the slope. Launching a rocket means beginning the long ascent toward the rim of the valley. Escaping completely means gaining enough energy to reach a place where the curvature flattens and the path continues outward forever. This is why the concept of escape velocity exists. It marks the energy needed to climb the curve until it no longer bends back. This vision of gravity is more than just elegant theory. It explains phenomena Newton's equations could not. The orbit of Mercury, for instance, wobbles subtly because it moves through a region of space where the Sun's curvature twists more sharply than predicted by Newton's model. Einstein's general theory of relativity accounted for that wobble precisely. It predicted that light from distant stars would bend around the Sun, a prediction confirmed during a solar eclipse in 1919. The bending of light revealed that even something massless can be guided by the shape of space-time itself. To describe gravity this way is to see the universe as dynamic and alive. Where there is no mass, space is flat. Where mass gathers, space sinks inward. Where immense mass compresses, in a neutron star or a black hole, space folds in on itself until even light cannot escape. Gravity is not a thread connecting distant objects. It is the terrain they inhabit. We move not through empty nothingness, but along an endless, ever-changing surface shaped by everything that exists. This understanding also shows why the deeper you are within a gravitational field, the more energy you must expend to climb free. It is not just about distance, but about depth within a curved landscape. A small planet like the Moon makes only a shallow dent in space-time, so escaping its influence is easy. The Earth's curvature is much deeper, and the Sun's deeper still. The very structure of the cosmos is a hierarchy of these wells, each nested within another. The Earth within the suns, the Sun within the galaxy within the universes. For humans standing on the surface of the Earth, gravity feels constant and familiar. It presses down with a steady hand, defining weight and motion. But in truth, it is not a force acting downward. It is the path that everything follows through curved space-time. When you drop a stone, it does not fall because something pulls it. It moves along the straightest possible path through the shape that Earth's mass has carved into the cosmos. You feel weight only because the ground prevents you from following that path. The revelation is both humbling and astonishing. It means that we are not separate from the structure of the universe. We are part of it. Every motion, from a falling leaf to a circling planet, follows the same geometry. Gravity is not an external power, but an intrinsic feature of existence. It is the conversation between matter and space, the dialogue that gives form to everything we see. And yet, for all its elegance, gravity remains the least understood of the fundamental interactions. We can describe it, predict it, and live within it, but we cannot yet unify it with the quantum rules that govern the microscopic world. Somewhere, in the interplay between particles and space-time, lies a deeper truth still hidden. Gravity may be the bridge between the tangible and the abstract, the key to a single, complete picture of the universe. As we continue to explore it, we begin to see why escaping it is such an achievement. It is not simply the act of overcoming a force, but of momentarily leaving the geometry that defines our existence. To climb out of the Earth's well is to move through the very curvature that binds atoms, oceans, and stars. It is to step beyond the deepest feature of reality itself, and to look back at it from the other side. In the curved landscape of space-time, nothing moves freely without consequence. The deeper the well, the steeper the climb. This truth defines every motion in the universe, from the slow drift of a comet to the furious ascent of a rocket. The Earth's gravity is not unusually strong by cosmic standards, yet it is deep enough that escaping it requires immense energy. To understand why, imagine space-time as a vast ocean. The mass of our planet creates a whirlpool in this ocean, and everything around it, the atmosphere, the satellites, even light itself, moves within its spiral. The closer you are to the center, the faster you must move to resist being drawn in. This is why the speed needed to stay in orbit increases as you move closer to the Earth's surface. Near the ground, gravity curves space sharply, demanding high velocity to remain suspended. Farther out, the curvature softens, and slower motion is enough to stay aloft. The International Space Station circles about 400 kilometers above the surface, moving at nearly 28,000 kilometers per hour. Any slower, and it would fall. Any faster, and it would rise into a higher orbit. What keeps it there is not an absence of gravity, but a perfect balance between speed and curvature. The station is always falling, yet never reaching the ground. This is one of gravity's great paradoxes. That motion can create freedom, even as the pull remains. Weightlessness in orbit does not mean gravity has vanished. It means everything inside the spacecraft shares the same curved path. Astronauts float because they too are falling, tracing the same trajectory as their vessel. The sensation of freedom is real, yet the invisible cage still surrounds them. It is only when a spacecraft reaches the threshold, where its speed allows it to climb the slope entirely, that it truly escapes. In Einstein's picture, energy and motion are two sides of the same coin. To move through a curved space-time is to spend energy reshaping one's trajectory. The deeper the curve, the more energy required to flatten it. This is why launching from smaller worlds is easier. On the Moon, where the gravitational well is shallow, a single strong push can send a craft outward with little resistance. On Earth, the curvature holds tighter, demanding far more fuel and precision. Each additional kilogram of mass means more energy needed to lift it, and the relationship is not linear, but exponential. This is the tyranny that engineers face every time a rocket leaves the pad. The cost of climbing the gravitational slope grows faster than intuition suggests. A vehicle twice as heavy does not need twice as much fuel. It needs many times more. That is because every drop of fuel adds weight, and that weight itself must be lifted, consuming even more fuel in a spiraling chain of demand. This cruel arithmetic is what makes spaceflight so difficult. To carry a small payload into orbit, most of the rocket must be fuel, destined to be burned and discarded before the mission truly begins. The engines roar, the tanks empty, and only a slender fraction survives to reach the quiet above. This challenge is compounded by the Earth's atmosphere. The air, thick and resistant, acts as a veil that must be pierced. At sea level, the pressure is immense compared to the vacuum of space. The rocket must first push through this dense ocean of molecules, losing speed and energy to drag and heat. The first minute of flight is a war against resistance. The engines not only lift the craft against gravity, but also carve a path through the invisible mass of air. As the altitude increases, the air thins and the struggle eases. But by then, most of the initial fuel has been consumed. All of this effort serves one purpose: to gain enough kinetic energy to reshape the craft's path through space-time. Once that energy surpasses the gravitational potential, the curvature can no longer pull the craft back. The slope flattens, and the vehicle transitions from falling toward Earth to gliding through the geometry of the solar system. The concept of potential and kinetic energy, first described by Newtonian mechanics and later reinterpreted through relativity, captures this perfectly. To climb away from the Earth's surface is to trade chemical energy for motion and height, to turn stored fuel into velocity that redefines the path through space-time. Yet the story does not end there. Even after a rocket has achieved escape velocity, it remains within the gravitational influence of larger bodies. The Sun's well envelops the Earth and all its satellites. The galaxy's curvature contains the Sun itself, binding every star in a vast, rotating disk. In the cosmic hierarchy of gravity, there is always a greater slope ahead. No object truly escapes. It simply moves from one curve to another, carried through the endless structure of the universe. This hierarchy is what gives the cosmos its shape. Stars orbit galactic centers not because they are bound by invisible cords, but because space-time itself curves inward under the weight of billions of suns. Galaxies cluster under their combined gravity, forming filaments and voids that stretch across the observable universe. On every scale, the pattern repeats. Wells within wells, curves within curves, from the orbit of electrons around nuclei to the slow drift of galaxies through intergalactic space. And in the middle of all these curves, we stand on our small blue world, feeling the weight of one particular well. Our sense of down, of weight, of motion, all are local expressions of a universal geometry. We live within this curvature as fish live within the sea, rarely noticing the medium that shapes our lives. Only when we leave it, when we look back and see the Earth suspended in the darkness, do we realize how deep our valley truly is. The realization is profound. Gravity is not merely a force to overcome, but the architecture of existence. It connects everything that has mass or energy, from the smallest particle to the largest cluster of galaxies. To understand it is to understand why stars shine, why planets form, and why the universe itself evolves the way it does. And it also explains why leaving our home requires such immense energy. We are not simply fighting a pull. We are climbing the contours of creation itself. Gravity does not merely shape space, it shapes time itself. This truth, uncovered through Einstein's equations, redefined the human understanding of the universe. In a gravitational field, time flows differently depending on depth. The deeper you are within a well, the slower time passes compared to regions farther out. This is not illusion or metaphor. It is measurable, testable, and real. Atomic clocks flown aboard satellites or carried aboard rockets tick at slightly different rates than those left on the ground. The closer a clock is to the center of Earth's mass, the slower its rhythm becomes. This stretching and compressing of time is one of gravity's most remarkable consequences. Imagine two observers, one standing on the surface of Earth and another floating far above, beyond most of the planet's curvature. Each believes time is passing normally for them, yet if they could compare notes, they would find that the one above experiences slightly more time between each heartbeat. The difference is tiny, but over long spans it becomes profound. If the observer were to descend toward a massive object like a black hole, the distortion would grow extreme. Time for that observer would slow almost to stillness, while the universe outside would seem to race ahead. On Earth, we live near the gentle bottom of a vast well, so we do not notice this effect in daily life, but it matters enormously in the precise mathematics of spaceflight. The satellites that make up global navigation systems orbit high above the surface, where time flows just a little faster. Engineers must correct for that difference. Otherwise, the positions they calculate would drift by kilometers each day. Every time your phone locates you, it is using relativity to account for the fact that clocks run differently in orbit than on the ground. Gravity bends not only the paths of rockets, but also the rhythm of existence itself. This connection between motion, energy, and time reveals another layer of the struggle to escape gravity. When a rocket accelerates upward, it is not just gaining height or speed, it is changing its relationship to time. It moves toward regions where space-time is less curved, where the flow of seconds runs a little quicker. In a poetic sense, the climb toward freedom is also a climb toward a faster universe. The energy spent in the engines is the cost of moving through gradients of both space and time. The interplay of these ideas shows why the energy needed for escape grows so sharply with mass. The deeper the curve, the greater the difference in time between top and bottom, and the more motion is required to climb through it. On smaller worlds like the Moon or Mars, the curvature is shallow, and time flows almost uniformly from surface to space. On Jupiter, the curve is so deep that its escape velocity reaches about 60 kilometers per second. No known chemical rocket could achieve that. Gravity there does not just hold, it dominates. Even within our solar system, these variations shape the architecture of planets and moons. Jupiter's immense gravity traps dozens of moons, each caught in its well. Some experience tidal stresses so strong that their interiors remain molten. Others, farther out, are bound loosely enough to dance in complex resonances, their orbits tuned to one another like instruments in a cosmic orchestra. All of these motions, from the smallest oscillation to the grandest revolution, are governed by one rule: the curvature of space-time caused by mass. Understanding this rule gives insight into why escaping Earth feels so costly. Our planet's mass carves a valley deep enough to hold an atmosphere yet shallow enough for life. That balance is rare. If the Earth were much smaller, it could not hold air or water. If it were much larger, its gravity might crush the bodies of living things or prevent chemical diversity. The same condition that makes life possible makes departure difficult. We evolved within this curvature, our muscles and bones tuned to its strength. Every leap, every stride, every heartbeat has been calibrated by 1 billion years of adaptation to this single gravity. To leave it, even for a short while, means defying not only physics, but biology. And yet, humanity has done it. We have climbed this slope and stepped briefly into the cosmic plane beyond. The first astronauts, looking down from orbit, saw the curvature of the Earth, not a line or a horizon, but a glowing arc against the blackness. They felt weightless, but they were still held. Gravity reached them even there, silent but unbroken. They orbited not because they had escaped, but because they had found a way to fall forever without ever hitting the ground. That continuous fall is the essence of orbit. Motion through curved space, so perfectly balanced that the downward and sideways tendencies cancel. The astronauts float because everything around them shares the same curve. They are not beyond gravity, but in harmony with it, like dancers moving to the rhythm of an unseen music. True escape requires more. Enough energy to rise beyond the curvature entirely, to let motion carry them outward without looping back. The energy for that, as we know, is enormous. The deeper insight is that gravity's grasp is not absolute. It weakens endlessly, but never vanishes. A spacecraft leaving Earth eventually feels more of the sun's pull than the planet's. Farther still, the gravity of the galaxy becomes dominant. Beyond that, there is the faint curvature caused by all the matter and energy in the cosmos. The chain never ends. Escape is always relative. a transition from one influence to another. We never leave gravity behind. We only trade one cage for a larger one. And yet, the act of trying matters. To rise from a world and see it as a whole is to understand the laws that govern it. Gravity, once a mysterious pull on an apple, becomes a window into the nature of reality. It ties together the falling of a stone and the collapse of a star, the ticking of a clock and the orbit of a galaxy. When we study it, we are not just learning about a force, we are studying the shape of existence, the architecture of motion, and the rhythm of time itself. In this understanding lies the reason why escaping Earth is so hard and so meaningful. We are creatures born in the depths of a gravitational well, made of matter forged in stars, held by the same geometry that curves the light of galaxies. To leave our planet is to climb out of that ancient shape, to look back and see the valley where life began. It is not an act of rebellion, but of comprehension, a statement that we have learned enough about gravity to use it, to navigate it, to momentarily rise above it. As we continue outward, we carry gravity with us, not as a prison, but as a teacher. It reminds us that motion and energy are intertwined, that freedom has a cost, and that every ascent must one day balance with a return. For in the end, even the most distant voyager still moves within the same grand curve, bound to the same laws that shape the fall of an apple. And perhaps that is the true beauty of gravity, not that it holds us down, but that it connects us to everything that ever was and everything that will ever be. There is a speed at which freedom begins. It is not a guess or a metaphor, but a precise threshold written into the laws of motion. At that speed, gravity's hold no longer bends a traveler's path back toward home. Any slower, and the journey will curve inward again. Any faster, and the craft will glide forever outward, never to return. That boundary, that sharp line between falling and escaping, lies at 11.2 kilometers per second. To understand what that number means, imagine it in human terms. 11.2 kilometers per second is roughly 40,000 kilometers per hour. A bullet fired from a rifle leaves the barrel at about 1.2 kilometers per second. The fastest passenger jet moves at less than 1 kilometer per second. A spacecraft must travel 33 times faster than a bullet to break free of Earth's grip. That number is not arbitrary. It emerges directly from the balance between energy of motion and the depth of the gravitational well that holds our world together. The logic behind it is simple to state, though its implications reach far. Every object on Earth sits at the bottom of a well carved by the planet's mass into the geometry of space-time. To escape, it must climb to infinite distance, to the point where the planet's curvature becomes so weak that its influence is effectively gone. The energy required for that climb equals the energy that binds the object to Earth in the first place. Kinetic energy must equal gravitational potential energy. Solve that relationship, and the answer becomes the escape velocity, a speed that depends only on the planet's mass and radius. For Earth, that balance yields 11.2 kilometers per second. No matter what direction one travels, no matter how clever the path, this requirement remains the same. One can reach it gradually through powered ascent or all at once through a single burst of acceleration. But without that total amount of energy, gravity will always win. The motion may carry a craft high above the atmosphere, even hundreds of kilometers into space, but unless the speed crosses that invisible threshold, the curve of its path will one day turn downward. Escape velocity is not unique to Earth. Every world has its own number. The Moon's is only 2.4 kilometers per second, so low that a simple engine can launch a small probe into space. Mars demands about 5 kilometers per second. Jupiter's is a staggering 60 kilometers per second, beyond anything our current rockets can deliver. These differences arise purely from mass and size. A dense, massive world carves a deeper curve in space-time, making the climb steeper and the required speed higher. Smaller, lighter bodies offer shallower slopes and easier freedom. For a rocket leaving Earth, the goal is not to reach that speed instantly, but to build it over time. Launch vehicles climb in stages, each stage burning its fuel and then falling away to lighten the load. But the process is a series of surrenders, shedding weight, releasing spent engines, discarding what can no longer contribute. The Saturn V, the mighty rocket that carried astronauts to the moon, stood more than 110 meters tall. Yet the small command module that returned to Earth accounted for less than 5% of its original mass. The rest was fuel and structure sacrificed to reach the necessary velocity. In those first moments of ascent, the rocket does not rise because it has escaped gravity, but because it pushes harder than gravity pulls. The engines produce thrust greater than the weight of the vehicle, lifting it slowly at first, then faster as fuel burns and mass falls away. Each second adds to its speed, gradually converting chemical energy into kinetic motion. When it reaches orbital velocity, about 7.9 kilometers per second, it is not yet free, but it is balanced. It circles Earth endlessly, falling sideways fast enough to miss the ground. To truly leave, it must accelerate further, gaining the extra energy that transforms orbit into departure. The idea of escape velocity helps explain why rockets follow curved paths rather than straight lines. Launching straight upward would fight gravity at every moment, wasting fuel. Instead, rockets tilt gradually, trading altitude for horizontal speed. The goal is not simply to go high, but to go fast, sideways, along the curve of the planet, until the path becomes a spiral that expands outward. Once the combined velocity reaches the magic number, gravity can no longer pull the craft back. The engines can finally rest. Even then, gravity does not vanish. It merely becomes too weak to dominate. The craft continues to slow as it climbs, converting motion back into potential energy, but it will never lose all its speed. Eventually, its path flattens into a near straight line, joining the wider geometry of the solar system. From that moment on, it is the sun's gravity that shapes its journey. The Earth's hold fades, replaced by a new and much larger curve. Escape is always relative. To leave one world is to fall into the embrace of another. The power needed to reach this speed is staggering. Accelerating 1 ton of mass to 11.2 kilometers per second requires more than 60 billion joules of energy. That is roughly the amount released by 15 tons of burning gasoline. For a full-scale launch vehicle carrying hundreds of tons, the total energy approaches that of a small nuclear explosion, all directed in one continuous push upward. This is why every launch appears both magnificent and violent. It is the visible transformation of chemical potential into freedom. Yet the number 11.2 is not absolute in the practical sense. Spacecraft can cheat the rule by taking advantage of motion already possessed by the Earth. Because the planet moves around the Sun at nearly 30 kilometers per second, any craft launched in the same direction automatically inherits that speed relative to the Sun. A spacecraft leaving Earth's orbit can therefore escape the solar system with less added velocity than the raw equation might suggest. Astronomers call this the Oberth effect, the art of using motion and gravity together to gain more energy than the fuel alone provides. This idea that one can borrow energy from motion is what allows interplanetary missions to succeed. When the Voyager probes left Earth, they did not blast directly into interstellar space. They first entered orbit around the Sun, then used the gravity of other planets to slingshot outward. Each encounter with Jupiter or Saturn stole a little of the planet's orbital momentum, accelerating the craft further until they reach speeds exceeding the solar escape velocity. Voyager 1 now travels beyond the Sun's influence entirely, still moving, still free, its journey powered not by fuel, but by geometry and timing. Escape velocity, then, is not merely a number. It is a symbol of the balance between energy and gravity, between confinement and flight. It represents the minimum cost of freedom in a universe where motion is always shaped by mass. To reach it is to cross an invisible line in space-time, the point where the curve of the world releases its grip and the traveler becomes, for a moment, unbound. For humanity, that moment is more than scientific achievement. It is an act of transformation. Every rocket that reaches escape velocity carries with it the story of our understanding, from Newton's apple to Einstein's curvature, from chemical fuel to celestial mechanics. It is proof that knowledge, applied with precision, can overcome even the deepest wells carved into the universe. When a spacecraft reaches that speed and the engines fall silent, what follows is the purest expression of motion. An object moving freely through the geometry of creation, guided only by the faint pulls of distant suns. And as it glides outward, one truth remains constant. It is still part of the same web of gravity, still bound to the cosmic fabric that connects all things. Escape is never absolute, but relative, a journey from one curve to another. Yet in that brief passage beyond the Earth's hold, in that crossing of 11.2 kilometers per second, lies the greatest expression of human will, the desire to rise, to explore, and to understand the universe that holds us all. To reach the magic number, a rocket must do more than generate speed. It must also survive the brutal arithmetic that governs every ascent. The path to 11.2 kilometers per second is written in the language of energy, mass, and exponential law. Every kilogram of payload requires fuel, and every kilogram of fuel adds more weight, which itself demands still more fuel. This endless loop is what engineers call the tyranny of the rocket equation. It is not poetic exaggeration, but cold mathematical truth. The equation describes how a rocket's change in velocity depends on the speed of its exhaust and the ratio of its starting mass to its ending mass. The larger the payload, or the lower the exhaust speed, the more propellant is needed. The relationship is exponential, meaning that small increases in required speed lead to vast increases in the fuel that must be carried. To gain 1 extra kilometer per second of velocity may demand twice as much propellant. To double the payload might require 4 times as much fuel. This law dictates the size, shape, and cost of every launch ever made. Imagine standing beside a launch vehicle before ignition. Nearly all the mass you see, more than 85%, is fuel. The sleek capsule at the top, the part that holds people or instruments, is only a tiny fraction of the whole. When the engines fire, those tanks begin to empty at astonishing speed. In a few minutes, hundreds of tons of liquid oxygen and hydrogen will be burned, producing the fire and thunder that push the vehicle skyward. What remains after the first stage is spent is lighter, faster, and one step closer to freedom. This process of discarding weight is essential. Without it, a rocket would carry dead mass that serves no purpose. The Saturn V, which carried the Apollo astronauts, rose from the pad with a mass of more than 2,900,000 kilograms. Its topmost section, the command module that splashed down in the ocean after the mission, weighed only about 5,000 kilograms. Everything else, the lower stages, the fuel tanks, the engines, was jettisoned along the way, falling back to Earth or burning up in the atmosphere. This is how humanity learned to fight gravity efficiently, not through raw strength, but through controlled sacrifice. The principle is elegant in its simplicity. To escape the planet, you must shed what no longer serves you. Each stage of a rocket is designed for a specific part of the climb. The first stage provides brute force, lifting the craft through the thickest layers of air where drag is strongest. The second takes over in the thinner upper atmosphere, where efficiency matters more than raw power. By the time the final stage ignites, the vehicle is already high above the world, carrying only a fraction of its original mass. The process is like climbing out of a deep well by dropping ballast with each upward leap. But the tyranny remains. Even the most advanced rockets today are constrained by the same equation that Tsiolkovsky derived more than a century ago. Engineers can improve efficiency by increasing exhaust velocity or reducing weight. but they can never escape the exponential nature of the problem. Each design is a compromise between ambition and limitation, between what physics allows and what materials can withstand. This is why spaceflight is still rare and expensive. Every launch is a negotiation with the unyielding logic of mathematics. To grasp how severe this tyranny is, consider this. The exhaust from a typical chemical rocket exits at about 3 kilometers per second. To reach orbit requires nearly 8 kilometers per second of change in velocity. That means the rocket must burn a mass of fuel many times greater than the mass of the final payload. If engineers could somehow double the exhaust speed, the required fuel would drop dramatically. But such propulsion systems remain difficult to build. Even small gains in efficiency demand revolutionary advances in chemistry and materials. This challenge defines the dream of next-generation propulsion. Ion engines, for example, achieve exhaust speeds of tens of kilometers per second by using electricity to accelerate charged particles. Their thrust is gentle, about the weight of a sheet of paper, but continuous. Over months or years, they can reach extraordinary speeds with minimal fuel. Such engines cannot lift rockets from the ground, but once in space, they become powerful tools for deep exploration. The spacecraft Dawn used this technology to travel between asteroids, achieving motion far beyond what chemical fuel could deliver. Despite these advances, the launch from Earth's surface remains a brute force endeavor. The lower atmosphere is unforgiving, and the first few minutes of ascent demand enormous thrust. The engines must overcome not only gravity's pull, but also the drag of air pressing against the vehicle's skin. The faster the rocket moves, the greater the friction and heat. Temperatures on the nose cone can exceed 1,000 degrees Celsius, and the structure must endure both aerodynamic pressure and vibration strong enough to tear metal apart. Each second of the climb is a delicate balance between power, control, and survival. As the rocket rises, the air thins and resistance drops. The engines can then focus entirely on adding speed rather than fighting drag. The craft begins to arc eastward, following the rotation of the planet to gain a small but valuable boost. By launching in this direction, rockets take advantage of Earth's own motion, adding about 460 meters per second to their velocity at the equator. Every bit helps, because every meter per second saved means less fuel, less mass, and lower cost. At last, when the final stage burns, the rocket nears orbital speed. The sensation inside the capsule shifts. The roaring vibration fades into silence. Outside the window, the blue of the atmosphere turns to darkness, and the horizon curves into a perfect arc. The Earth below seems to drift, though in truth, both planet and spacecraft are moving at tremendous speed. The astronauts feel weightless, not because gravity has ceased, but because they are falling around the Earth in unending descent. To push beyond this balance, to reach the full 11.2 kilometers per second, the engines must fire once more. This time not to circle the planet, but to depart from it. The thrust tilts the orbit outward, stretching it until it becomes a long ellipse that no longer closes upon itself. When the spacecraft reaches the top of this path, its velocity carries it onward into open space. The last traces of air vanish, the pull of Earth fades, and the ship becomes a traveler of the solar system. In that moment, the tyranny of the rocket equation meets its purpose. All the calculations, the stages, the fuel, and the sacrifice converge into motion. The vehicle coasts freely now, no longer burning, no longer straining. It is the embodiment of potential turned kinetic, of energy transformed into escape. The roar of engines has given way to silence, but in that silence lies victory, the triumph of understanding over the constraints of nature. And yet, even here, far above the world, gravity continues to whisper. The sun's well waits ahead, vast and deep, and the next chapter of motion begins. For in this universe, there is no end to falling, only new centers around which to dance. The first 100 kilometers are the crucible where dreams meet resistance. Every launch, no matter how advanced, begins in the same struggle, against gravity against atmosphere, against the relentless friction of air and the precision demanded by physics. This region, so small compared to the vastness of space, holds the fiercest opposition to flight. Rockets do not truly face the emptiness of the cosmos until they have conquered the weight and pressure of their own world. In those opening moments, the rocket stands motionless, engines trembling with restrained fury. Then ignition, a burst of flame and sound that shakes the ground like thunder. The pressure of exhaust gases erupts downward, and only when their force exceeds the weight of the entire vehicle does motion begin. The first movement upward is hesitant, almost fragile. The rocket climbs a few meters per second, as if testing whether it can truly defy the planet that made it. In that brief hesitation lies the essence of the human condition, the decision to rise, even when gravity insists otherwise. The air near the ground is thick and unyielding. It resists motion with a force proportional to the square of speed, meaning that doubling velocity multiplies drag by 4. Every increase in thrust must contend not only with gravity, but also with this invisible ocean of molecules pushing back. As the rocket accelerates, shock waves ripple along its surface. The structure vibrates, straining against forces that would tear apart anything less than perfect. Engineers call this region max Q, the point of maximum dynamic pressure, when aerodynamic stress reaches its peak. The rocket throttles down slightly to survive this moment, sacrificing acceleration to preserve itself. Inside the capsule, astronauts feel the weight of gravity multiplied. Their seats press hard against their backs. Every breath becomes labor. The acceleration feels like an invisible giant pushing them down into their chairs. The gauges tremble. The view outside blurs into a bright haze of flame and cloud. For several minutes, the entire vehicle is consumed in a balance of forces. Engines driving upward, atmosphere pushing downward, gravity tugging from below. Every second demands perfection. Beyond 20 kilometers, the air begins to thin. Drag diminishes, the engines regain full power, and the rocket accelerates more efficiently. The sound outside fades as the dense air gives way to silence. The blue of the sky deepens to indigo. The flames of the engines no longer dance orange and red, but turn into pure white light. The vehicle now moves faster than a rifle bullet, its motion smooth but relentless. At 50 kilometers, the atmosphere is almost gone. Air resistance drops to a fraction of what it was at launch. The engines no longer need to fight the suffocating pressure of the lower layers, yet gravity's pull remains almost the same. Contrary to what intuition suggests, the strength of Earth's gravity decreases only slightly with altitude. Even 100 kilometers above the surface, it is still about 97% as strong as at sea level. The rocket must still pour energy into acceleration, fighting a force that never truly fades. This altitude marks the boundary known as the Kármán line, the place where air is too thin for aerodynamic flight, where lift can no longer support wings. Above this invisible border lies what we call space, though in truth, space begins nowhere and everywhere. It is a gradual transition from air to vacuum, from blue to black, from resistance to freedom. The rocket, having survived the worst of the climb, now begins to tilt its path along the horizon. Its engines push less upward and more sideways, building the horizontal velocity required for orbit. In these moments, the balance shifts. The fight against the air is over, but the race for speed begins. The engines continue to roar, converting the last of the propellant into motion. The acceleration presses the astronauts down with unrelenting force. 3 times their weight, sometimes more. The world outside curves visibly, revealing the delicate boundary between Earth and the void. The line between night and day arcs across the surface below, a sharp divide between sunlit ocean and shadowed land. Then, suddenly, the engines cut off. The roar becomes silence. The pressure vanishes. Objects inside the capsule drift upward, suspended. The astronauts' arms, their pens, even droplets of water float freely. The sense of up and down dissolves. They are no longer climbing, they are falling, but falling around the Earth instead of back toward it. The speed they achieved is enough to keep missing the ground, tracing a circle around the planet. The weight they felt a moment ago was never gone. It has simply been redirected into perpetual motion. Outside the window, the Earth glows against the blackness of space. Its colors are impossibly vivid. Blue oceans, white clouds, thin amber edges of atmosphere glowing like firelight. Below lies the place they left, bound by gravity, now silent and small. The fragility of that view stirs something beyond science, a recognition that we are all held by the same invisible hand, all part of the same delicate balance. The first 100 kilometers mark a threshold, not just of physics, but of perception. Beneath lies the realm of air, weather, and life. Above lies the realm of stars, silence, and infinity. Crossing that boundary requires unimaginable power, yet once it is crossed, motion becomes effortless. The rocket that struggled against resistance now coasts freely. The engines rest, the laws of motion take over, and the vehicle glides around the world, following the curve of gravity's geometry. From here, space seems serene, but every orbit is a constant fall. The astronauts float not because gravity has ended, but because everything around them moves in harmony. They are part of a grand choreography, the mathematics of balance, the physics of falling forever. Gravity holds them as gently as it holds the moon, guiding their path with silent precision. To reach this point is to witness both the power and the tenderness of nature. Gravity, the same force that crushes mountains into valleys, now cradles the ship in perfect motion. The same equation that resists flight also enables the orbit that sustains it. Escaping Earth is not a battle won, but a balance found, a momentary truce with the laws that bind the cosmos. And yet, beyond this delicate equilibrium lies the next challenge, the path from orbit to true escape. For to remain here is to fall forever. To leave, one must move faster still, adding the final measure of energy that will carry the craft beyond the reach of the planet's curve, into the endless domain of the sun. Every flight from Earth is an act of mathematics. Behind the fire, the noise, and the glory, there is a quiet, unbreakable rule that governs every ascent. It is an equation so simple that it can fit on a single line, yet so powerful that it has defined every space mission in history. It tells engineers what is possible, what is impossible, and what price must be paid for every kilogram carried skyward. It is called the rocket equation, a law discovered by a visionary mind long before rockets ever left the ground. In the late 19th century, Konstantin Tsiolkovsky, a schoolteacher in Russia, spent his nights imagining machines that could rise beyond the atmosphere. At a time when even airplanes did not exist, he conceived of metal towers filled with propellant that would burn and push themselves into the heavens. To make his dream precise, he sought the mathematics of motion under constant thrust. What he found was both profound and merciless. The velocity a rocket can achieve depends on only two things: the speed of its exhaust and the ratio between its starting mass and its final mass. This ratio, written simply as a fraction of what the rocket weighs before launch compared to after it has burned its fuel, reveals the tyranny. Each increase in velocity demands exponentially more propellant. The heavier the payload, or the greater the desired speed, the more fuel must be carried. But that extra fuel itself adds weight, which in turn demands even more fuel to lift it. The result is a chain without mercy. Every improvement brings a new burden. Every advantage is bought at staggering cost. For example, if a rocket engine expels exhaust gases at 3 kilometers per second, a good value for chemical propellants, and the craft needs to reach 8 kilometers per second to enter orbit, the fuel must make up nearly 90% of the rocket's initial mass. To reach escape velocity, 11.2 kilometers per second, the required proportion grows even higher. Almost everything that leaves the launch pad must be fuel. The spacecraft itself, along with its passengers or instruments, accounts for only a small fraction of the total. This is why rockets look the way they do, tall, narrow and hollow, designed to hold as much propellant as possible. It is why engineers divide launches into stages. Each stage acts like a disposable ladder rung, used once and thrown away. The first stage lifts the rocket through the lower atmosphere, fighting gravity and drag with brute force. When its fuel is spent, it is dropped to fall back into the ocean, lightening the load. The next stage ignites, carrying the remaining mass higher and faster. Only by discarding empty tanks can the rocket continue climbing efficiently. Without staging, no chemical rocket could ever reach orbit. The Saturn V, the largest rocket ever flown by humanity, demonstrated this principle perfectly. Its first stage alone held more than 2,200 tons of fuel and burned for just 2.5 minutes. The second stage carried about half that amount and burned for 6 minutes more. By the time the final stage fired, the entire vehicle weighed less than 1/10 of what it did at launch. That final burn carried a small capsule, a fragile human habitat, to the moon. The same logic governs every launch today. The Falcon 9, the Ariane 5, the Starship, all obey Tsiolkovsky's equation. Modern engines are more efficient, materials lighter, computers smarter, but the exponential law remains untouched. The rocket equation is not a challenge that can be conquered. It is a truth that must be respected. Even in an age of reusable boosters and precision landings, every kilogram that reaches orbit still costs energy measured in billions of joules. The reason is simple. Rockets do not push against air or ground. They push against their own exhaust. When the engines ignite, fuel is burned and expelled at high velocity, and the reaction drives the rocket forward. The faster the exhaust, the greater the thrust for a given mass of fuel. This is why new technologies aim to increase exhaust velocity, to squeeze more motion out of every drop of propellant. But even here, there are limits. Chemical reactions release only a finite amount of energy. To go beyond, engineers must turn to electricity, nuclear power, or fusion, each with its own complexity and risk. Consider the challenge faced by the designers of interplanetary missions. A probe sent to Mars must first reach orbit, then accelerate again to leave Earth, and finally slow down to enter Mars's gravity well. Every one of these steps costs velocity, and each meter per second adds to the fuel required. The smallest increase in mission mass can ripple backward through the design, forcing larger tanks, stronger engines, and heavier structures. The exponential spiral tightens, and costs climb to astronomical levels. Tsiolkovsky understood this even in his time. He dreamed of multi-stage rockets long before any had been built. He imagined space stations and refueling depots, knowing that continuous launches from Earth's surface would always be inefficient. In his notes, he wrote a simple truth that has echoed through every generation of engineers since. Earth is the cradle of humanity, but one cannot live in the cradle forever. He understood that escaping the cradle would never be easy, but that it would define what it means to be human, to reach beyond the limits of our birth. The tyranny of the rocket equation is not only mathematical, it is philosophical. It reminds us that progress comes with cost, that every ascent demands surrender. To lift something precious, people, instruments, ideas, we must cast off what no longer serves. A rocket's discarded stages are monuments to this truth. They fall away and burn, sacrificed so that something lighter may rise. The process mirrors life itself, an upward struggle through gravity's pull, shedding weight to find freedom. And yet, within this tyranny lies a kind of grace. The equation does not forbid flight, it simply demands precision. It forces us to understand the balance of energy, to design with care, to think beyond brute force. Every rocket that succeeds is a triumph not over gravity, but over ignorance. It is a testament to the human ability to take the most unforgiving law of motion and turn it into an instrument of escape. Even with all our knowledge, the cost of leaving Earth remains immense. Each launch consumes hundreds of tons of fuel. Each mission requires years of preparation. But in the fire and thunder of every ascent, there is beauty. The expression of a species that learned to turn mathematics into motion, to trade mass for momentum, to climb from the well of its own world using nothing but understanding. The tyranny of the rocket equation endures, but so does our determination. We have not yet found a way to defeat it, but we have learned to live within its limits, to make art out of constraint. Every time a rocket rises and the sky trembles, it is the equation made visible. A line of algebra turned into flame and flight. And beyond that, flame, beyond the noise and the weight, waits the next challenge. For even when the rocket leaves the ground, gravity continues its pull, and the air itself becomes a final adversary. To reach space is not just to fight mathematics, but to fight the world's very breath. The moment a rocket leaves the pad, it enters a contest with the air, a contest that no creature evolved to fight, and that only machines of staggering power can endure. The atmosphere that sustains life becomes a wall against flight. Each layer resists motion, pressing down with invisible weight, feeding turbulence, friction, and heat. What we call the sky is not an empty passage, but a fluid ocean of nitrogen, oxygen, and water vapor, all stacked and restless. To climb through it requires more than thrust. It requires resilience against the world itself. In the first seconds of ascent, the rocket moves slowly. Thrust barely exceeds weight, and the craft seems to hover, flames roiling below as if chained to the ground. It must overcome both the downward pull of gravity and the resistance of air pressing back against every square meter of its surface. Each breath of atmosphere has mass, and that mass must be pushed aside. For an object moving at thousands of kilometers per hour, that resistance becomes immense. Engineers design rockets not only to generate thrust, but also to survive the punishing assault of air density and speed. The journey upward is a symphony of forces. Gravity pulls downward with a nearly constant acceleration of 9.8 meters per second squared. Air drag increases with the square of velocity. Thrust declines slightly as the rocket climbs, because the exhaust expands into thinner air. The balance of these variables changes second by second. At low altitude, pressure and density dominate. At high altitude, gravity and inertia rule. Between them lies a narrow region of chaos, a thin boundary where the rocket faces its greatest trial. This region is called max Q, the point of maximum dynamic pressure. It occurs roughly 1 minute after liftoff, when the rocket has accelerated enough for air resistance to peak before the atmosphere begins to thin. The stress on the structure is tremendous. Panels strain, joints creak, vibrations ripple through the frame. Engineers throttle down the engines just before this point to prevent damage, then increase thrust again once the rocket passes through. If the craft can survive max Q, the worst of the atmosphere is behind it. To an observer watching from the ground, the rocket's path may seem smooth, but inside the capsule, it is a tempest of motion. The noise, though muffled, is overwhelming. The airframe groans under the constant assault of aerodynamic forces. Astronauts feel the weight of acceleration as their bodies are pressed into their seats with several times the force of gravity. Their vision narrows, their breathing becomes shallow, their hearts labor to pump blood against the pressure. Yet through it all, training and trust hold firm. The roar outside is proof that the engines are still alive, that physics is still obeyed. As the rocket rises higher, the atmosphere begins to thin rapidly. By 50 kilometers, air density has dropped to less than 1% of its value at sea level. Drag weakens, the sky darkens, and the pressure on the hull eases. The engines regain efficiency, no longer wasting energy compressing air that pushes back. The rocket's acceleration increases, and the climb becomes smoother, faster, and eerily silent. The craft has pierced the veil. Below it, clouds stretch in vast white plains. Above, the black of space begins to show through, but even as drag fades, gravity's hand remains heavy. a rocket's engines must work continuously just to maintain upward speed. The moment thrust ceases, the craft begins to fall. This is the great irony of flight. Altitude alone does not mean freedom. As long as the rocket's velocity remains below orbital speed, it is still bound to Earth's curvature. The air may be thin, but the planet's pull is still almost as strong as it was at launch. To truly escape requires not just height, but speed. Motion sideways, not upward, fast enough that the path of fall curves into the horizon. The cost of this climb is staggering. The energy required to push a rocket through the first 100 kilometers exceeds that needed to travel thousands of kilometers in space. The atmosphere, so fragile in thickness compared to the planet's size, is the hardest barrier we know. It is the reason why launches consume vast quantities of fuel in minutes, why the first stage of any rocket is the largest and most powerful. Once above the air, the craft glides with ease, but reaching that place is like swimming through molten glass, slow, punishing, and exacting. The air that resists rockets is the same air that makes life possible. It scatters sunlight, forms clouds, and carries the breath of every living thing. Its density and pressure protect Earth from meteors and radiation. Yet these same gifts impose the greatest challenge to flight. The boundary between resistance and freedom is thin, 100 kilometers of transition where air becomes void. The Kármán line, named for the scientist who defined it, marks this edge. Beyond it, wings cease to function. There is no lift, only inertia and thrust. Crossing that threshold is the moment of transformation. The engines roar against nothingness, and the sound begins to fade. Vibrations ease, acceleration steadies, and then suddenly, the sky turns black. The curve of the Earth appears below, edged with a fragile band of blue, the last breath of atmosphere, thin as smoke. The astronauts are weightless, not because gravity has vanished, but because everything around them shares the same free fall. They look down and see a world bounded by air. That faint blue layer, no thicker than the skin of an apple compared to the size of the Earth, holds every storm, every forest, every living thing. From space, it seems impossibly delicate. The rocket has fought through it with brute strength, but the view reminds the travelers that strength alone cannot sustain life. What holds them now is not power, but momentum. The graceful balance of speed and fall. This is why engineers speak of the first 100 kilometers as the wall. Beyond it lies the near-perfect vacuum of space, where motion endures without resistance, where a single burst of energy can carry a ship for centuries. But to reach it, humanity must first win a war against the air itself, a war fought in seconds with precision measured to the heartbeat. The hardest part of spaceflight, then, is not space. It is the world we come from, dense, turbulent, and beautiful. Every launch is a confrontation with that beauty, a reminder that the atmosphere that nurtures us also confines us. And yet, in conquering it, we do not destroy it, we honor it. The fire and thunder of rockets are the echo of Earth's breath, transformed into a scent. Once the engines fall silent and the craft drifts above the clouds, the fight is over. The planet's pull still reaches out, but it no longer commands. The air no longer burns or resists. The spacecraft glides within the gentle geometry of orbit, falling forever and never falling at all. The tyranny of the rocket equation, the drag of air, the pull of gravity. All are still present, but they now serve a new purpose. They are the conditions of existence, the backdrop to freedom. From here, the journey outward can begin. The rocket that fought its way through resistance now becomes a satellite, a traveler, a seed of human will cast into the void. But as it circles the world below, one truth remains. Gravity has not been defeated, only understood. The illusion of weightlessness is among the most misunderstood sensations in all of physics. From the outside, it looks as if astronauts floating in orbit have escaped gravity. as if the pull of Earth no longer reaches them. But the truth is the opposite. Gravity remains nearly as strong at the altitude of the International Space Station as it is on the surface. What has changed is not the force, but the motion, a perfect dance where falling becomes flight. A spacecraft in orbit is forever falling. Its engines have given it such speed that as it falls toward the planet, the curvature of Earth itself falls away beneath it. The two motions, downward toward the center of gravity and sideways around it, balance perfectly. Every second, the station drops about 5 meters, but the Earth curves away by the same amount. The result is endless descent that never meets the ground. Weightlessness, then, is not the absence of gravity, but the constant surrender to it. Inside the capsule, everything shares the same acceleration. The floor, the walls, the air, the people. All fall together. Because there is no surface resisting the pull, there is no sensation of weight. Objects drift, not because gravity is gone, but because every part of their world is moving through the same curved path in space-time. This is what Einstein described as free fall, the purest state of motion possible in the universe. The sensation is both liberating and strange. Astronauts describe it as perpetual flight, a slow and graceful drift that feels more like swimming than floating. Muscles relax, bones feel light, but orientation disappears. Up and down lose meaning. There is only motion and stillness, coexisting in perfect balance. Yet this freedom hides complexity. To stay in orbit, the spacecraft must maintain precise speed and altitude. The slightest drag from the remnants of the atmosphere can slow it, causing the path to decay. Without occasional boosts from thrusters or visiting ships, even the largest station would eventually spiral back toward Earth and burn in the atmosphere it once escaped. This delicate balance between falling and staying defines the frontier of human spaceflight. The same physics that holds satellites in orbit governs the moons of Jupiter, the rings of Saturn, and the paths of galaxies around their dark centers. Gravity shapes every circle in the sky. It is both the sculptor and the cage, the reason motion persists, and the reason escape demands so much. Orbit is the beginning of freedom, not its end. To truly leave Earth behind, a craft must push beyond the circular dance and climb the slope of the gravitational well until the planet's influence fades into the sun's. That step requires more than velocity, it requires vision. Engineers must plan trajectories that weave through invisible fields, using motion itself as fuel. A spacecraft leaving low orbit adds energy through short, precise bursts of thrust. Each burn stretches the orbit into an ellipse that extends farther and farther from Earth, until one end of that ellipse no longer returns. The path from orbit to escape is like walking along the edge of a deep bowl. Near the bottom, small steps do little to raise altitude, but as the climb continues, each new stride carries farther. By the time the spacecraft nears the rim, a single push can send it gliding outward, free of the curve. The transition is subtle, not dramatic. There is no line, no sound, no moment of crossing. The craft simply continues moving until Earth becomes another star in the background. For interplanetary missions, timing and geometry become everything. The Earth's motion around the Sun provides an enormous share of the necessary energy. Launch windows are chosen so that the rocket departs when the alignment of planets allows the most efficient path. These windows may open only once every few years. Miss it, and the next chance may not come soon. The fuel saved by precision can determine whether a mission succeeds or fails. Even in these outer stages, the tyranny of the rocket equation lingers. Every gram of propellant used to escape orbit was carried up through atmosphere and gravity, adding to the cost. Engineers therefore use nature's own motion whenever possible. They plan gravity assists, slingshot maneuvers that borrow energy from planets. By falling toward a massive world and swinging past it, a spacecraft can gain speed without burning fuel. The planet loses an infinitesimal amount of orbital energy, while the craft gains freedom. The Voyager probes used this method to leap from one planet to the next, escaping the solar system entirely. All of this, orbit, escape, and the quiet falling of satellites, reveals gravity's true nature. It is not merely a downward pull, but a bending of the stage on which all motion occurs. When we orbit, we trace the lines of that curvature, surfing the contours of space-time carved by mass. The cost of escape is the cost of climbing that geometry. Rockets do not fight a force so much as they reshape the path they follow, turning a circle into a line that extends toward infinity. And yet, in this grand mechanics, there is something deeply human. Every orbit, every escape, begins with the same desire that once led us to climb trees and mountains. The urge to see farther, to rise above the limits of the familiar. Gravity defines those limits, but it also gives meaning to their conquest. Without its pull, there would be no challenge, no ascent, no triumph. In the silence of orbit, as the Earth turns below in slow majesty, the laws of physics and the story of humanity merge. The rocket equation, the curve of space-time, the balance of fall and flight. They are all chapters of the same narrative, the tale of a species that learned to understand the universe by trying to leave it. The climb to space begins not with silence and stars, but with resistance. The thick, unseen mass of air pressing back against every motion. The Earth's atmosphere is a shield, a fragile but powerful ocean of gases that protects life and punishes flight. Every rocket that rises must carve a path through this barrier, and the first few minutes of ascent remain the hardest journey ever undertaken by any machine. At launch, thrust must overcome two enemies at once, gravity pulling downward and drag pushing backward. The lower atmosphere is dense, chaotic, and full of motion. Air molecules strike the rocket in billions of collisions per second, heating its skin, shaking its structure, and slowing its climb. The faster the rocket moves, the stronger the resistance grows, rising with the square of velocity. To double the speed is to quadruple the punishment. The rocket's engines must roar with unimaginable power simply to keep accelerating through the wall of air that wraps the planet. The atmosphere is not uniform. It thins gradually as altitude increases, but the transition is uneven, marked by turbulence and layers that shift with weather and heat. Each kilometer changes the conditions of flight. Below 10 kilometers, air behaves like a fluid river. Above 50, it behaves more like smoke. Between these extremes, the rocket faces unpredictable crosswinds and shear forces that can twist its frame. Engineers spend years modeling these invisible threats because a single structural failure during ascent can destroy an entire mission. The point of greatest stress comes about a minute after liftoff, known as max Q, the moment when aerodynamic pressure reaches its peak. The engines throttle back to protect the rocket from tearing itself apart. Then, as air thins and pressure drops, they throttle up again. Every launch passes through this needle's eye. It is the moment where engineering precision meets the limits of the material world. Beyond it, drag diminishes rapidly, and the sky begins to open. As the rocket climbs past 30 kilometers, the blue fades to black. The curve of Earth becomes visible below. The engines now work more efficiently because there is less air to fight. The noise softens, the vibration steadies, and the ship begins to arc eastward, following the rotation of the planet. The climb becomes less vertical, more graceful. The goal is no longer to rise, but to accelerate, to build horizontal speed fast enough that the craft begins to fall around the Earth instead of back toward it. At 100 kilometers, the Kármán line is crossed, the boundary we call the edge of space. Here, air is so thin that wings no longer work. There is no longer a medium for lift, no drag to slow the motion. Yet even here, traces of atmosphere remain, enough to tug faintly on satellites and space stations. The International Space Station, circling at about 400 kilometers altitude, must periodically fire its engines to counteract this drag. Without those small pushes, it would gradually spiral downward and burn in the air it once escaped. This invisible friction is a constant reminder that freedom from gravity and air is never absolute. Even in orbit, resistance endures. The last atoms of the atmosphere, heated by sunlight, expand and reach upward, brushing against the hulls of spacecraft. Solar storms can swell the upper atmosphere, increasing drag and shortening satellite lifespans. In the cosmic scale, this resistance is gentle, but it never fully disappears. It is a whisper of the world below, reaching even into the vacuum above. The first 100 kilometers of ascent consume more fuel, energy, and risk than the entire remainder of a space mission. Once free of drag, motion becomes effortless. But below that threshold, every meter gained is a struggle against the mass of the air. This is why rockets must be so powerful and why they seem to lift so slowly at first. Each stage burns with fury, not to gain distance, but to overcome the crushing inertia of the lower atmosphere. And yet, in that battle lies beauty. The same air that resists ascent is what makes sunsets glow red, what carries sound, and what sustains breath. The struggle through it is the price of life itself. When a rocket bursts free of the last traces of blue sky and enters the black, it carries with it the memory of that resistance, the mark of its origin. Spaceflight is not a rejection of Earth, but an extension of it. The energy that lifts a rocket upward is the same energy that drives wind, rain, and waves. The only difference is direction. Beyond the atmosphere, the concept of drag gives way to new kinds of motion: orbits, transfers, and escapes. A rocket that has mastered the climb must now master the curve of space itself. For even though air is gone, gravity remains, shaping every trajectory. Freedom from resistance does not mean freedom from nature. It means the start of a new kind of balance, one defined by velocity and curvature, rather than pressure and lift. Every launch that clears the atmosphere marks the same victory, the triumph of precision over chaos. To pass through the storm and reach silence is to prove understanding. Humanity's greatest journeys begin not in peace, but in fire, thunder, and resistance. The noise fades only after the battle is won. Orbit is not freedom from gravity. It is gravity made visible. Every satellite, every station, every astronaut circling the Earth remains inside the planet's grasp. They do not float above gravity, but within it, tracing paths that exist only because of its pull. The International Space Station, for all its majesty, is still falling. A continuous descent that never ends because the ground curves away beneath it. To stay in orbit, an object must move sideways fast enough that its fall matches the planet's curvature. For low Earth orbit, that speed is about 7.9 kilometers per second. Any slower, and the orbit decays. Any faster, and the orbit stretches higher. Perfect balance is achieved when centrifugal motion, the tendency of mass to move in a straight line, exactly counters the inward pull of gravity. The result is perpetual free fall. Not absence of gravity, but complete surrender to it. The sensation of weightlessness that astronauts feel is the purest form of free fall. Inside their capsule, everything, bodies, air, and equipment, accelerates toward Earth at the same rate. There is no opposing surface to create the sensation of weight. Yet if the station were to stop moving sideways, it would plunge into the atmosphere within minutes. Gravity's grip is as strong in orbit as it is on the surface. Only the path has changed. To truly escape Earth, one must exceed orbital speed by about 3 kilometers per second, reaching the full 11.2 kilometers per second required for freedom. That extra energy transforms the curved path of an orbit into an open trajectory, a line that extends forever outward. Once that threshold is crossed, the spacecraft becomes bound, not to Earth, but to the Sun. Even then, gravity remains. The Sun's pull takes over, drawing the craft into a new orbit, one that might circle the Sun itself, or intersect the orbits of other planets. Interplanetary missions rely on this transfer of dominance, trading one gravity well for another. Spacecraft use precise bursts of thrust to reshape their trajectories, falling toward one world and away from another in a celestial dance choreographed by mathematics. Sometimes, gravity can be used as a tool rather than an obstacle. By passing near a planet, a spacecraft can steal a tiny amount of its orbital momentum, accelerating outward in what is called a gravity assist. The Voyager probes use this method to travel from Jupiter to Saturn, then to Uranus and Neptune, gaining speed at each encounter without burning fuel. It is a cosmic slingshot, proof that the same force that holds us down can also propel us forward, if understood correctly. Orbit, then, is not escape. It is a state of compromise, a delicate agreement between motion and attraction. The Moon orbits Earth for the same reason the Earth orbits the Sun, because falling forever is easier than leaving entirely. Escape requires energy that exceeds the potential of the well. Orbit merely balances it. Humanity's presence in orbit is therefore not freedom, but preparation. The space station, the satellites, and the probes that circle our world are practice for departure. They live within gravity's domain, learning its rhythm, waiting for the moment when engines will fire one final time and the curved path will open into the straight. In this way, orbit represents not the end of the climb, but the beginning of the journey. To circle Earth is to remain tethered to it by an invisible cord, feeling the pull of home even while suspended in darkness. True escape lies beyond, in the thin line between motion and freedom, where gravity still whispers but no longer commands. Gravity never ends. It weakens with distance, yes, but it stretches infinitely, threading through every corner of space. Even at the edge of the solar system, far beyond the planets, the faint tug of the sun still reaches outward, shaping the paths of comets and dust. Earth, too, exerts its influence far beyond the sky we see, an invisible hand extending millions of kilometers into the void. The region where Earth's gravity dominates over the sun's is known as the Hill sphere. It marks the outermost boundary, where our planet can hold onto moons or satellites before the greater pull of the sun takes control. For Earth, that sphere extends roughly 1.5 million kilometers in every direction, almost 4 times farther than the moon's orbit. Within this bubble, Earth is the master. Beyond it, the sun rules. This interplay of overlapping gravity wells defines the architecture of the solar system. Each planet carves out its own domain within the sun's greater field. The moon, for example, dances inside Earth's Hill sphere, orbiting our planet, even as both together circle the sun. The delicate balance between these pulls keeps celestial bodies in their steady rhythms, a cosmic hierarchy of control and surrender. Imagine space not as emptiness, but as a landscape of invisible slopes and valleys. The deeper a well, the harder it is to climb out. Earth's well is deep enough to hold its atmosphere and moon. The sun's well is so immense that even light, though not slowed by mass, bends as it passes by. The galaxy itself forms a grander well still, containing billions of stars, each with its own family of smaller curves nested inside. Everything falls into something larger. This idea that there is no true escape, only transition, reshapes how we think of space travel. A spacecraft that leaves Earth's orbit does not become free. It simply moves from one gravitational influence to another. Once beyond Earth's Hill sphere, the sun's pull dictates its path. To leave the solar system entirely, as Voyager 1 and 2 have done, a probe must gain enough energy to exceed even the sun's escape velocity. At that scale, freedom demands not kilometers per second, but tens of thousands of them. Voyager 1 achieved this through careful use of the solar system's structure. Launched in the late 1970s, it used Jupiter and Saturn as stepping stones, each gravitational encounter flinging it faster outward. By the time it passed Neptune's orbit, it was moving at over 17 kilometers per second relative to the Sun, fast enough to climb the slope of the solar well forever. Even now, decades later, it continues to coast through interstellar space, still feeling the sun's pull, but never to return. The same geometry that governs these great missions also holds sway over everything closer to home. The tides that rise and fall along Earth's shores are the daily expression of the moon's gravitational pull, stretching the planet's oceans. The sun adds its rhythm, creating the cycles of spring and neap tides. The same invisible curves that shape the paths of planets also shape the breathing of our seas. Gravity is not distant, it is intimate, continuous, woven into every motion of matter and life. If we could see gravity, the universe would appear as a vast web of depressions and peaks, every mass curving the fabric of space around it. Earth's well would look like a smooth funnel, the moon's a smaller ripple orbiting within it. The sun's funnel would dwarf them both, encompassing the entire solar system. Each star in the galaxy contributes to this cosmic sculpture, their combined influence bending the shape of the Milky Way itself. This endless reach of gravity explains why the universe is structured the way it is. Stars gather into clusters, clusters form galaxies, galaxies bind into filaments that stretch across the cosmic web. Even the vast voids between them are not empty. They are the highlands between gravity's valleys. The same principle that keeps the moon in orbit also binds galaxies billions of light years apart. In this hierarchy, there is no absolute freedom. Every object is caught within the influence of something greater. The moon orbits Earth. Earth orbits the sun. The sun orbits the center of the Milky Way, and the galaxy itself moves through the gravitational field of the universe's invisible dark matter. Motion without attachment does not exist. Every journey is a fall within some larger curve. Yet, within these constraints lies the key to exploration. By understanding the geometry of gravity, humanity has learned to navigate it. Spacecraft use planetary wells as stepping stones, diving into them to gain speed and climbing out again with borrowed momentum. This dance of falling and rising allows missions to reach places that raw power alone could never achieve. The gravity that once held us captive now serves as an ally, a cosmic current we can learn to ride. Even in the vastness beyond planets and stars, gravity's whisper remains. It connects everything to everything else, linking atoms to galaxies in a single continuous law. It does not fade into nothingness. It merely becomes gentler, its hand still guiding, its reach still infinite. To escape one gravity well is to enter another, but that does not diminish the meaning of flight. Each escape expands our understanding, widens the circle of our motion, and brings us closer to seeing the universe as it truly is, not a collection of separate bodies, but a single connected whole bound together by the most patient and persistent force of all. Humanity has always sought cleverness over brute strength. The same mind that once shaped stones into tools now shapes equations into trajectories, finding ways to outthink nature rather than overpower it. In spaceflight, this philosophy has become essential. The energy required to leave Earth is so immense that no amount of fuel can make the journey simple. To explore the solar system, we had to learn how to use gravity itself as a partner, a force not just to fight, but to guide, bend, and borrow from. The first principle of this art is efficiency. To move from one orbit to another, a spacecraft does not burn its engines continuously. Instead, it uses short, precise bursts at the right moments, letting momentum do the rest. This technique, known as a Hohmann transfer orbit, allows a craft to shift between circular paths around a central body. For example, from Earth's orbit to Mars's, using the least possible energy. The idea is simple. Burn once to rise into an elongated orbit, then burn again when reaching the farthest point to circularize around the target. Two small pushes, perfectly timed, can replace the waste of constant acceleration. This same logic governs how satellites reposition themselves around Earth. They do not force their way through space, but coast along the curves carved by gravity, touching their engines only to reshape those curves slightly. Every change in direction or speed is a conversation with the invisible geometry of space-time, a request, not a demand. The most successful missions are those that speak this language fluently. Beyond Hohmann transfers lies an even more ingenious method, the gravity assist, also called the slingshot maneuver. It uses the motion of planets themselves as sources of momentum. A spacecraft, approaching a planet from behind, falls into its gravity well, accelerating as it descends. When it swings past and escapes, it carries away part of the planet's orbital motion around the Sun. The planet slows by an imperceptible amount, while the spacecraft gains enormous speed. No extra fuel is burned. Only timing and trajectory matter. The first use of this technique in deep space came during the 1970s with the Mariner and Voyager missions. By carefully plotting paths through the alignments of the outer planets, engineers turned gravity into a highway. Voyager 2, for instance, used Jupiter's massive pull to reach Saturn, Saturn's to reach Uranus, and Uranus's to reach Neptune, a cascade of assists that carried it to the edge of the solar system. What began as a set of equations on paper became a demonstration that the universe itself could help us travel if we learned its rhythm. Other strategies take this relationship even further. Lagrange points, for example, are regions of balance where the gravity of two massive bodies, such as Earth and the Sun, precisely cancel each other. At these points, a spacecraft can hover with minimal effort, remaining in stable relative position while orbiting with both bodies. The James Webb Space Telescope now rests at one such point, 1.5 million kilometers from Earth, using subtle thruster adjustments to maintain its place in this gravitational equilibrium. It is not stationary in an absolute sense. Nothing in space truly is, but from our perspective, it floats effortlessly between forces, balanced on the edge of two wells. These techniques reveal a deeper truth. Motion through space is not a battle, but a collaboration. Gravity is not an enemy to conquer, but a tide to navigate. The solar system is full of these tides, invisible currents flowing between planets, moons, and the Sun. Mathematicians and mission planners map them as interplanetary superhighways, networks of gravitational routes where energy requirements are low and travel is efficient. A spacecraft following one of these natural paths may take longer to reach its destination, but it uses far less fuel, gliding along the fabric of space-time like a leaf on a cosmic stream. The dream of escaping smarter also includes visions of future technology. Ion propulsion, already tested on several missions, replaces the violent blast of chemical rockets with a continuous gentle push. It uses electricity to accelerate ions, charged particles, to speeds far greater than any combustion exhaust. The thrust is weak, but it never stops. Over months and years, the acceleration builds, and the spacecraft achieves extraordinary velocity with astonishing efficiency. This method, slow but tireless, reflects a new way of thinking, power through patience. Even bolder ideas stretch the imagination further. The concept of a space elevator, for instance, proposes anchoring a cable from Earth's surface to a station beyond geostationary orbit, about 36,000 kilometers above the planet. Objects could climb this tether slowly, powered by electricity rather than rockets, bypassing the need for enormous fuel loads. The physics is sound, but the materials required, something stronger than any known fiber, remain beyond current technology. Still, the idea persists, a symbol of how humanity seeks to turn gravity itself into architecture. Other proposals look beyond chemical and electric engines to nuclear and fusion drives. A nuclear thermal rocket could heat propellant with a reactor, doubling or tripling exhaust speed compared to chemical fuel. A fusion drive, if ever realized, could provide constant acceleration across interplanetary distances, shrinking travel times from months to days. These concepts embody the same principle as every earlier innovation. Find more efficient ways to shape the geometry of motion, to trade raw force for elegance. Yet, no matter how advanced the technology becomes, the underlying challenge remains unchanged. The energy required to climb out of gravity's well is dictated by the same laws that Tsiolkovsky discovered over a century ago. There are no shortcuts around physics, only smarter ways to work within its rules. The art of escape, then, lies in understanding the shape of the universe deeply enough to use it to our advantage. In this sense, the story of space travel is not a story of defiance, but of harmony. Every successful mission is an act of cooperation with nature's laws. Rockets rise, planets pull, and trajectories curve in perfect balance. When a spacecraft slingshots past a planet or rests in a Lagrange point, it is not breaking the rules of gravity, but playing them like music, transforming necessity into art. The smarter we become, the more we realize that true escape is not about brute speed or endless fuel. It is about grace, the ability to move with the currents of the cosmos, to understand when to push and when to let go. The universe rewards not force, but finesse. Every world in the solar system lives beneath its own invisible weight. The strength of that weight, the pull of gravity, defines everything that happens upon its surface. It shapes landscapes, atmospheres, oceans, and even the bodies of those who might walk upon it. To understand why escaping Earth is so difficult, one must see how unique its gravity truly is when compared to the rest of the worlds around the Sun. Start with the Moon, our closest companion. Its gravity is only 1/6 that of Earth. A person who weighs 70 kilograms on Earth would weigh barely 12 on the lunar surface. A stone thrown there travels farther, arcs slower, and falls with a lazy grace. The airless sky offers no drag, and the horizon feels strangely near because the world beneath is so small. To leave it requires far less energy, only 2.4 kilometers per second of velocity compared to Earth's 11.2. A small rocket, even one that fits in a garage on Earth, could send a craft from the Moon into orbit or out toward the stars. This is why future missions may one day use the Moon as a stepping stone for deep space exploration. Its weaker gravity well makes departure economical. Its surface a natural launch pad into the greater solar system. Mars sits between the extremes. Its gravity is about 1/3 of Earth's, enough to hold a thin atmosphere, but not enough to keep it dense or warm. Escaping Mars demands a velocity of 5 kilometers per second. A challenge, but far less than what Earth demands. A rocket leaving from Mars could reach orbit with a fraction of the fuel required here. The lower gravity would also make construction and transport easier. For this reason, many scientists imagine Mars as the first home beyond Earth, a world where humanity could build, explore, and launch outward with greater freedom. But farther outward, the challenge becomes monstrous. Jupiter, the giant of the solar system, possesses a gravity so intense that no known technology could launch from its surface, even if it had one solid enough to stand on. Its escape velocity is about 60 kilometers per second, more than 5 times faster than Earth's, and beyond the reach of any chemical propulsion we have ever built. Even its moons live under this vast grip. To escape from Io or Europa, one must also contend with Jupiter's massive field pulling backward. A ship leaving such a world would need not only power, but precision, using orbital mechanics to slingshot outward rather than fight directly. By contrast, the smaller worlds, Mercury, Pluto, and the asteroids, barely hold their surface materials at all. A spacecraft could leap from them with a modest push. On some asteroids, an astronaut who jumped with enough strength could leave the body entirely and drift into space. Their escape velocities are measured not in kilometers per second, but in meters per second. These places are almost weightless, fragile in their grip on matter, reminders that gravity exists on a spectrum from immense to almost non-existent. Earth stands at the balance point. Its gravity is strong enough to hold oceans and air, to shape weather and sustain life, yet gentle enough to allow motion, flight, and exploration. It binds the moon, tethers satellites, and stabilizes climate through the steady pull that defines day and night. It is both protector and warden. Too little gravity, and a planet cannot keep its water. Too much, and it traps everything beneath unbearable pressure. Earth's value lies in its perfection. Not too light, not too heavy, an equilibrium rare among worlds. This balance, however, is also why escaping it is so costly. The same gravity that keeps us alive resists our departure with unrelenting strength. Rockets must climb a slope that life itself has spent billions of years adapting to. Every bone, muscle, and organ in the human body evolved under the weight of 9.8 meters per second squared. In microgravity, those same systems weaken and drift toward disorder. Even our biology bears the imprint of this planet's pull, as if every cell remembers which way is down. The contrast between worlds paints a picture of cosmic diversity shaped by a single law. On Mercury, the sun's heat burns the day side to 400 degrees Celsius, yet its weak gravity allows atoms to escape into space with ease. On Venus, gravity nearly matches Earth's, but the dense atmosphere and crushing pressure make escape doubly hard. On Mars, dust storms swirl in a thin air that cannot hold warmth. On Titan, Saturn's largest moon, gravity is low, but the thick nitrogen atmosphere offers strange buoyancy. A person there could strap on wings and fly by muscle power alone. The difference in gravity also means a difference in destiny. Smaller worlds are easier to leave but harder to live on. Larger ones are easier to live upon but harder to escape. Humanity's expansion into space will therefore move first toward the middle ground, the moons, the asteroids, and Mars. Worlds light enough to release us, yet solid enough to sustain us. In that sense, the dream of interplanetary travel is less about conquering gravity and more about choosing the right partner among its many forms. Yet, gravity's reach goes beyond the physical. It shapes culture, thought, and imagination. Every myth of flight, from ancient wings to modern rockets, arises from the same instinct: to break free of the weight that holds us. And still, we are bound by it. Even when we stand on another world, even when we leap across its sky, gravity will still be there, calling us home in its silent, endless pull. Among all the planets, Earth remains the one that teaches us both the difficulty and the meaning of escape. Its grip challenges our engines, but it also forged our will. Every world offers a different lesson about motion, balance, and freedom, but all return to the same truth. Gravity is universal, impartial, and eternal. It can be weaker or stronger, but it can never be absent. To live anywhere in the cosmos is to live within its reach. And so, when humanity finally spreads beyond Earth, hopping from moon to planet to star, we will carry gravity with us, not as a burden, but as memory. The weight of our home will remain in our bones, the rhythm of its fall in our hearts. For gravity is not the enemy of flight, it is the reason flight has meaning. Every launch begins the same way: a spark, a roar, a trembling rise against the weight of the world. Yet every launch also carries something unseen, the echo of a question older than science itself. Why do we reach upward? What drives a species born in the dust to fling itself toward the stars? The answer lies in the very force we struggle to overcome. Gravity does not just hold us down, it gives us something to rise against. For billions of years, gravity has been the sculptor of everything we know. It gathered dust into planets, gas into stars, and stars into galaxies. It ignited the sun, forged the metals in our blood, and shaped the very surface of the earth we walk upon. Without it, there would be no world, no light, no life. We exist because gravity gathered the chaos of the early universe into order. Yet to grow conscious within that order is to feel its constraint. The same pull that created us became the first obstacle our minds ever recognized. Escaping Earth's gravity, then, is not just a matter of physics. It is a story of curiosity, defiance, and understanding. When humanity first looked up and saw the sun and stars, The force that held us to the ground also defined the distance between us and the infinite. Every myth of flight, every winged god, every soaring dream, was born from the desire to rise above the invisible chain that connects us to this planet. The invention of rockets turned that dream into law-bound reality, a marriage of imagination and mathematics that allowed the impossible to become measurable. Yet the true victory of spaceflight is not in escaping gravity, but in comprehending it. We have learned that it is not a force pulling from a distance, but the curvature of space-time itself, a shape that mass and energy create, a geometry in which we move. When we send a spacecraft into orbit, we are not breaking free from gravity. We are learning to move within its design. To master flight is to understand the shape of the universe, to find harmony within the very thing that once felt like imprisonment. In this light, every rocket launch becomes more than an engineering achievement. It becomes a symbol of evolution. Life on Earth began in the oceans, rose to the land, and learned to walk upright. Each step away from the ground was a victory over gravity, small but cumulative. Birds took to the air, defying the pull through lift and motion. Humans followed, first with balloons, then wings, then engines, until finally we reached the edge of the atmosphere and beyond. The rocket is not a break from this story. It is its latest chapter, a machine that embodies the dream of all creatures that ever leapt or flew. The irony is that gravity, our eternal adversary, has been our greatest teacher. Every lesson in motion, every equation of physics, every discovery in astronomy depends on understanding how it works. Newton's apple revealed the universality of the law. The same pull that makes a fruit fall governs the orbit of the moon. Einstein deepened that truth, showing that gravity is not a tug, but a twist in the fabric of reality. In the end, the force that binds us to the ground also connects us to the cosmos. It is not local, but universal. Every act of escape is, in fact, an act of connection. Even now, as spacecraft leave Earth and journey outward, they do not truly leave gravity behind. They simply enter larger patterns. The moon pulls on Earth, Earth on the sun on the galaxy, and the galaxy on the unseen dark matter that surrounds it all. Motion is never isolated. Every trajectory is woven into a greater whole. The escape from one well is only the beginning of a fall into another, stretching endlessly across space and time. But this does not diminish the meaning of escape. It enhances it. To rise from one level of the cosmic structure to another is to move toward understanding, to see more of the pattern, to grasp a little more of what reality truly is. We climb the ladder of gravity not to conquer it, but to explore the infinite architecture it has built. Each launch, each orbit, each distant mission is another rung on that ladder. From the first fire that lit a primitive rocket in ancient China to the great engines of Saturn V and Starship, humanity's ascent has always been both scientific and spiritual. The physics remains unchanged, chemical bonds breaking, gases expanding, energy converting into motion, but the meaning has evolved. When a rocket leaves the pad and the roar fades into the thin air above, what follows is not just the silence of space, but the echo of our species, realizing its place in the universe. Gravity keeps us rooted, yet it also keeps us honest. It reminds us that freedom has a cost and that energy must always be paid. It binds us to home, but also points us outward, whispering that beyond this well lies another and another still. We rise because we are drawn, not away from gravity, but through it, along the paths it has already carved through space-time. In that way, every ascent is not a rebellion, but an act of alignment with the cosmos. Perhaps that is why we will never stop trying to rise. The struggle against gravity is also the story of intelligence itself, of life growing aware enough to see the invisible and curious enough to chase it. It is the tension between weight and will, between the laws that hold us and the minds that seek to understand them. To escape gravity is to prove that knowledge can rewrite destiny, that comprehension can turn constraint into possibility. When future generations look back on this era, they may see our rockets not as weapons or tools, but as symbols, monuments to the moment a small, fragile species learned to stand up against the fundamental curve of the universe and say, "We understand." Every plume of fire, every trail of smoke is a signature written in light across the sky, declaring that the children of gravity have learned to shape their own fall. And so the story comes full circle. Gravity built our world, and in fighting it, we found ourselves. Every launch that breaks the silence of the morning sky carries not only metal and fuel, but meaning, the collective defiance of billions of years of stillness. To escape gravity is not to abandon Earth, but to celebrate it, to prove that from its pull came strength, and from its weight came wonder. Every rocket that leaves Earth carries more than fuel. It carries defiance. Gravity built our world, but it also gave us something to rise against. To escape it is not to reject the planet that birthed us, but to understand it fully, to honor the laws of nature by using them to reach beyond their limits. In the end, we do not escape gravity, we fulfill its purpose.